All right, so part 2 is about the area in the plane. So we're going to look at areas enclosed by polar curves. That's enclosed, okay, not under like what we've been doing before. So these problems work a little differently in polar coordinates, and this is kind of like a sketch that will tell you what I mean. So here's the idea of polar curves. With polar curves, we're dealing with angles. And um, therefore, we're not going to be based on rectangles because we're not going down to the x-axis or over to the y. We're going to be slicing this up from the pole. So if you slice this up from the pole, and I put a GeoGebra image that you can kind of play around with to see why this works exactly. Okay, so we use infinite numbers of sectors to find the area. So remember from pre-calc what a sector was? Not even pre-calc, it was actually 10th grade. But a sector was like a slice of pizza. So that's what we're doing here is we're taking basically a slice of pizza from the curve, but the difference is that the top part of the curve is not always going to be perfect. But if you integrate, if you take small enough pieces from the pole all the way across, then the curve starts looking more and more, the difference starts looking more and more like a circle. And like I said, I can't really, you guys know I'm not a very good drawer, but there is a GeoGebra animation that will show you exactly what I'm talking about. So it ends up looking like a circular sector if we take small enough slices. And remember, our integration is going to be now between two different angles rather than two different x values. And if you remember that the area of a sector of a circle was given by area equals half theta r squared, where theta is in radians, important for calculator, and our area is bounded by the two radial lines, the two angles of alpha and beta. So this right here is a you must know, like never forget, formula. So the area is equal to half the integral from alpha to beta of r squared d theta. And honestly, if you remember this formula, then really these problems are really easy. They're not that hard. Okay, so here's our first example. Oh, so this is important to remember that this is an integral of areal differential. That means dA is equal to half r squared d theta. Take a look at the fundamental theorem of calculus to remember that. All right, so we're going to find the area of a region inside a cardioid where r equals a, and a is going to be any number greater than 0. So really, for this specific problem, what a is, as long as it's bigger than 0, it doesn't really matter, okay? Times 1 plus cosine of theta. So I'm going to just choose a number for a. So 3, 1 plus cosine of theta. So that's going to be my example. And we know that it's a cardioid, and we know that it's reflected over the x-axis. So my image, just to have a quick image in my head, remember that this is going to look like 3 plus 3 cosine of theta. So my image is going to be out to 6, 1, 2, 3, 4, 5, 6. And the smallest radius is going to be at 0, and then up here is 3, 3, so there's my cardioid. Okay? And if you remember that the theta for a cardioid is from 0 to 2 pi. So guess why this is important to remember for cardioids? Is because this is going to be our alpha and this is going to be our beta. Because we want to find the area of the whole entire cardioid from 0 all the way to 2 pi. So now that we know this, basically it's just a matter of using the formula. So A equals 1/2 0 to 2 pi of r squared, and in this case our r is going to be 3 times 1 plus cosine theta squared d theta. And now the rest of this is just going to be doing simple math. Before we move on, let's take out this 3 if we can, but remember, you're not really taking out a 3, you're taking out a 3 squared. So you're taking out a 9 from 0 to 2 pi, and we're left with 1 plus cosine theta squared d theta. Now you can use the calculator and you get the approximation 42.412 units squared for the area, and if not, then you can use U substitution to integrate this, and you can still do this by hand. So this is not a calculator based problem, but just for time's sake in the video I'm making it that way. Now keep in mind that most polar equations are symmetrical, correct? Either to the x-axis or to the y-axis. So if you had a problem that said to set up the integral, yes, this is correct right here. This setup is correct. This setup is correct. But you can also have a symmetry setup. Answer. Because we know that the area up here is equal to the area down here. So they could even trick you in saying that, all right, it's 2 times 1/2 the integral from 0 to pi. So it's just split in half of 3 times 1 plus cosine of theta squared. So what's the only difference between these two? Is that the bounds are different, but because of that, this one is multiplied by 2. So yes, that could possibly be an answer. So if you see that on a quiz, do not come up to me and tell me the answer is not there. And then of course, if you clean this up a little bit, you will end up with 0 to pi, because what happens to 2 times 1/2? 3 times 1 plus cosine theta squared d theta. Or you can have 9, right? So all of these are possible answers based on symmetry. All right, next one is easy. Find the area of the region inside the oval Lie Mason of r equals 4 plus 2 cosine of theta. So really what we have to remember is that a Lie Mason, this is going to be a dimpled one, but we have to remember that the theta for a Lie Mason is from 0 to 2 pi. Now almost all of them are 0 to 2 pi except for the circles that we did in the beginning, and then the petals with, let me remind myself, it was the petals with the even coefficient in front of sine or cosine. But we'll come back to that if a problem comes up. So if we remember this, then we have area equals 0 to 2 pi of 1/2. And remember, you can write the 1/2 on the outside or on the inside. It really doesn't matter because eventually you're going to take it out. 2 cosine theta squared d theta. If you do this in the calculator, you get 56.548. Can you do this without a calculator? Absolutely. So it's not going to be just a calculator-based problem. All right, to find the area of a region given in the diagram below, which lies between two polar curves, So this is what we mean. We have a sector from alpha to beta. Okay, so this angle right here, theta is alpha, but this angle right here is theta equals beta. So this is beta and this is alpha. Okay, so keep in mind that when we say beta, it's not just this angle in here, it's going to be from the axis all the way up. And we have two polar curves. So the first polar curve is right there, and then the second polar curve, let's call it right there. And we want to find the area in between these two polar curves. So let's call this guy right here R2 and then this guy right here R1. All we do is we subtract the integrals from each other. So very similar to what we used to do before. Okay, so we're going to subtract the two integrals from each other to basically figure out the two parts. So if it was just R2 in this picture, it would be the area of this whole entire thing, correct? And if it was just R1 in this picture, it would be the area right down here. So if we find the area of the whole entire thing and take away the area of this part right here, then what are we left with? The area that's in between those two curves. So here's the formula that we're going to be using. You can use whichever one suits you best, but it's basically going to be the area of the outer curve, which makes sense, right? Because you have to find the area of the whole thing first, and then you're going to subtract it from the area of the inner curve. So, two ways to do this, whichever one you like best. Just remember that it's going to be the outer squared minus the inner squared. Alright, let's do some examples. So let's find the area of the region inside of the circle. R equals 3a cosine of theta, and outside of the cardioid, R equals a, 1 plus cosine of theta, where a is greater than 0. Oops. Where a is greater than 0. Okay? So just to make things a little bit easier, I'm going to let a equal 1 for this specific problem. Now, they won't always give you the examples like that. They'll usually tell you what a is. But if they don't, pick an a. So my two curves are going to be R1 is 3 cosine of theta, and my R2 is going to be 1 plus cosine of theta. Now, I didn't just randomly pick these. The reason I picked R1 is because this says find the area of the region inside of the circle. So that means this guy's going to be my outer, this guy's going to be my, my first curve. I see what I did in my example. Alright, I did randomly just give these two guys numbers, but we'll number them properly in the picture. Okay, so my picture is going to look like this. So I have a circle with 3 cosine of theta, which basically means that it's a circle that starts at the polar axes and goes up a radius of 3. Okay, and outside the cardioid of 1 plus cosine of theta. So because it's a cardioid, then my radius is going to be 1 plus 1, which is 2. And my inner radius is going to be 0. So it's a cardioid, and then this goes up to 1. So the cardioid goes like this, comes in, goes like this, goes out. And then they want us to find the area of the region inside of the circle, so inside this circle, but outside the cardioid. So we want to focus on this region right here. So the way that you're going to think about this is, which one is my outer circle? My outer is going to be, this is my outer, and then this part right here, that is my inner polar function. Okay? So my outer is actually R1, and my inner is going to be R2, but it really doesn't matter what you number it. I mean, as long as you know which one's your outer, which one's your inner. Now, the trick here is, we got to find the points of intersection, so that that is what our bounds are going to be. Okay? Because we're focusing at a specific point. We're not going all the way around. So, so we can't use the actual domain of the polar graph, because then we'll just be subtracting the whole entire thing. Okay? So we want to find the points of intersection of the two, and this is an easy algebraic problem. 3 cosine of theta equals 1 plus cosine of theta, right? You set them equal to each other and see where they are equal. You solve this, so we get 2 cosine of theta, right? I subtracted 1 cosine of theta equals 1. So cosine of theta equals 1/2. And where is cosine of theta equal to 1/2? It's from at pi over 3 and at 5 pi over 3. So I'm going to use the symmetry. Okay, I'm going to use the symmetry part because both of these guys are cosine. So I just figured out that this right here is pi over 3, and this right here is 5 pi over 3. Okay, so I'm not going to use the 5 pi over 3, I'm just going to double my whole entire area equation. So here my area is going to be 2 times the integral from 0 to pi over 3, because it's the top part and the bottom part. And then I'm going to use the 1/2 times my outer, which is 3 cosine of theta squared, right? My outer, which is the circle, minus my inner, which is going to be 1 plus cosine theta squared d theta. And yes, this can also be done without a calculator. You can pull out the 1/2. So we actually end up with area equals 0 to pi over 3 of what can we say? 9 cosine squared theta minus, this would need more foiling, 1 plus cosine squared theta, squared d theta. And this definitely gets ugly, okay, to do it by hand, but it is possible. And you end up with an answer of pi. Okay, just for the sake of not having 2 20-minute videos, we're going to do that. Alright, the parametric length formula from section 10.1 can also give us the polar curve. Now this is important because it's a little different than our other equation, but we're still using our how should I say this? The independent variable, the dependent variable and the derivative of the dependent variable, just like before. Okay? So this is our equation for polar curves. So keeping this equation in mind, find the length of the curve r equals theta squared from 0 to square root of 5. So this gives us the limits of the integral. And this curve is theta squared from 0 to square root of 5, and basically tells us that at 0, at theta, if theta is 0, it's going to be 0 squared, so my radius is 0. At pi over 2, because that is less than square root of 5, so I can find pi over 2, so pi over 2 squared, it's a little bit above 3, and then it'll be best if you graph this in the calculator, but you can get a nice picture that kind of looks like this. Alright, all the way to -10. At -10, but it actually is going to be 10, so you would graph it as a positive. Makes sense? So for square root of 5 squared is going to be 10. Okay? Alright, so how do we start this? We know that r is theta squared. This is just a picture. If you graph this in the calculator and take your bounds from 0 to square root of 5, this is the picture that you would get. And we want to find the length of that curve. And then we know that dr d theta, because we need both of those for our equation, we know that dr d theta is going to be 2 theta. And now we know that the length from 0 to square root of 5 is going to be r squared, which is theta squared squared, plus dr d theta, which is 2 theta squared d theta. And then we can start solving this. So first we simplify, so this is theta to the 4th plus 4 theta squared d theta. And yes, you can do this without a calculator. Because we're at 22 minutes, I'm just going to show you my work over here for this problem. So basically, I factored out a theta squared, and the reason I did that is because I can now split up this into theta squared times theta squared plus 4, and what is the square root of theta squared? We get just theta. And we're left in here with just theta squared plus 4. And the reason why this is important is because now you can use U substitution and say, alright, if U equals theta squared plus 4, can I get du to be theta times d theta to get rid of this part? And yeah, du is going to be 2 theta du. Move the 2 over, and we are able to replace the theta d theta and the theta squared plus 4. So, and of course we can't forget about the 1/2. So now we got 0 to square root of 5 plus square root of u, and then the rest is just plugging and getting our final answer. Alright, I'm gonna put up with this section two worksheets. Okay, they look long, but honestly you don't have to do all of them. See, this one right here is just specifically about polar area, but I like this worksheet because it has free response questions that are directly from the AP exam, and multiple choice questions that are directly from the AP exam. So, and it tells you when you can use the calculator and when you cannot use the calculator. Now this second worksheet right here is good because it covers everything else. So really, if you wanted to, number 6, for example, is covered on the other worksheet, so you don't have to do those. The other parts are not, and it's a review of 10.5, and it has length. And it also has 2 questions that are directly from the AP exam that you can practice. So I'm going to put these 2 up, but you really, for finding the area, just stick with this, because this is more than enough examples on how to find the area. Okay? There are some problems on here that are not covered, which was finding the horizontal and vertical tangents. I'll look up some problems in the textbook that will look like that, but if I do forget to give you guys some numbers, just remember that this example was number 9 on page 566, so most likely number 8 and number 10 are going to be exactly the same, so you can practice those. Okay? Because I don't have a textbook at home to even look at, and I only have the online book, which is a little different than ours. Alright, good luck and enjoy the rest of your break.